This is an AIPMT question in electric charges and fields. It's a regular question in so many exams too, very interesting question. It says a charge q, small q, placed at the center of line joining of two exactly equal positive charges, capital Q. So, he is saying that there is two charges q, positive charges, equal charges q, they were separated by a certain distance placed at the center of the line joining of exactly two equal and opposite charges. So he is saying that placed at the center of the line joining, in the middle of the line joining. Anyway, I will prove it. I don't take that into consideration because I just want to explain things. A small q is placed. The system of three charges in equilibrium. Be careful. All these three charges has to be in equilibrium. Then what must be the charge that small q is equal to? First of all, let's assume a positive charge is placed. When plus q is placed in between. On that plus q, this capital Q applies a repulsion because this is also positive. This capital Q also applies a repulsion, this is also positive. So, Q is in equilibrium, plus Q is in equilibrium. It has no problem, it is definitely in equilibrium. But in our problem, every charge, all charges of the system has to be in equilibrium. For that to happen, let us consider the plus Q, any other charge. On this plus Q, what we have to consider as plus Q, we apply a repulsion. On this plus Q, who is also a positive charge, also applies a repulsion. Both these forces are in the same direction and hence they won't cancel each other. And hence plus Q can't be in equilibrium. So, you cannot keep a positive charge between two other positive charges and expect the entire system to be in equilibrium. That middle charge can be equilibrium, but the entire system cannot be equilibrium. So, let me see what happens when I keep a negative charge in between them. So, we have plus Q, another plus Q, in between let us keep a negative charge. On this negative charge, this positive charge applies a attraction. This positive charge also applies a attraction. So, when minus Q is placed, minus Q can be in equilibrium, as these two forces can cancel at a particular condition. Look at the plus Q, this plus Q. On this plus Q, this minus Q applies a attraction towards it. On this plus Q applies a repulsion. So, they too also can cancel because the forces are acting in opposite direction when their magnitudes are equal. That implies Q's also can be in equilibrium. So, the first thing that you need to understand is, in between you have to keep a negative charge, not a positive charge. So, definitely these two options are wrong. I need not even look into that further, they are wrong. I have to identify one answer in between these two. So, let us see where is that, where do we have to keep it, right. Let minus Q is placed somewhere. So, plus Q, in between a minus Q is placed at a distance x. So, this distance becomes d minus x, assuming that the total distance is d. So, on this negative charge, this positive charge applies a attraction, this positive charge also experience a attraction. So, for minus q to be in equilibrium, force between this and this 1 by 4 pi epsilon naught q minus q by x square equal to force between this and this, that is middle and the last, right, q and minus q by d minus x whole square. 1 by 4 pi epsilon naught and all this will cancel. So, d minus x whole square equal to x square, take a square root on both sides, d minus x equal to x, that implies d equal to 2x, x equal to d by 2. So, he has given at the center, it means he is at the middle. So, you have to keep this charge at the middle, d by 2, the other distance also d by 2, then only the system can be in equilibrium, otherwise system cannot be in equilibrium. Now, I have to calculate how much is that charge is, what is that charge that we have kept. For that, let us consider that other charges of these edges q to be in equilibrium. So, what I have to say, plus q, another plus q, in between I have kept a minus q. Forces acting on this plus q I want to calculate. On this plus q, due to this minus q, there is a force of attraction, who is at a distance d by 2 as we have proved. How much is that? 1 by 4 pi epsilon naught minus q and q by d by 2 whole square. Again, on this plus q also applies a repulsion because both are positive charges. What is the force between this capital Q and this capital Q? So that this capital Q is in equilibrium when these two forces are equal, Q and Q by this entire distance between these two is d square. So 1 by 4 pi epsilon naught can be cancelled, capital Q can be cancelled, minus q by d square by 4 equal to q by d square, minus 4q by d square equal to q by d square. I have just taken this 4 into the numerator, d square and d square will cancel. That implies small q equal to minus q by 4. That is what our answer is, right. So, it is a very interesting question. You get lot of concepts while you are solving the question, and you talk about equilibriums, right. The most important thing that I want to tell you is, when he says 3 charges or the system has to be in equilibrium, each of the charges, not only the middle charge, the other 2 charges in the system also have to be in equilibrium. That means the resultant force acting on that each charge has to be 0. That means there shall be forces of equal magnitude, but opposite direction acting on that. That is very important. I want you to get that point. I might have solved this problem in the earlier years also, but anyway I have solved afresh just to make it, just to tell you that how important it is. That is it. Thank you for watching.